Okay, let's say you won the lottery and you're given two very different options. So the first option is that you're going to get $5,000 on the first day and then $1,000 more every day. So you'll get $6,000 and $7,000 and $8,000 until March 31st. That's one option. The other option is that you will get a penny, just a penny on the first day, but it will double every day. You'll get 2 cents on March 1st, and then 4 cents, and then 8 cents. So it says to make a table for the amount of money that you would get. So option A, remember you got $5,000 technically on what would have been day 0, and then you're adding $1,000 every day. Okay, so we're going to keep adding 1,000. We go from 9,000, 10,000, 11, 12, 13, 14. So go ahead and write that down. Also, keep in mind as you're writing this down that this is not the total amount of money that you would have. You would have 5,000 plus 6,000 plus 7,000 because you're adding on every day. So by March 10th, you'd have quite a bit of money with option A. Okay, let's look at option B. You start out with a penny, but then it is doubling, and we have 2 cents and 4 cents and 8 cents. So we do not have a lot of money here. Let's go ahead and start doubling it. So 8 cents would double to 16, and then 32 cents, then 64. So we still don't even have a dollar yet. $1.28, finally over a dollar. $2.56, $5.12, $10.24. So same thing over here. It would add up. You wouldn't just have $10. You would add all of this up. Okay, so think about which option you would choose. Would you go with option A? I would probably, by looking at this, go with option A because, look, you've got way more money than over here. You've just got this $10.24. It says to continue the calculations in your calculator. So go ahead and grab your calculator. Okay, and what we're going to do for option A, I'm going to put the 15,000 in the calculator. And what am I doing? I am adding 1,000. So this is March 11th. Then I'm adding 1,000. This is March 12th. After you do the same thing in the calculator twice, you only have to press enter. So that's March 12th, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and March 31st, it says you would get $36,000. Okay, which is a really good, really nice amount of money, especially considering that we would add all of the money you've gotten the day before. So this definitely is looking like the better option. Let's come over here for March 10th. I'm going to start with the $10.24, and I'm going to double it. So that's March 11th. Double it, March 12th. Once you've put the same thing in the calculator twice, you could just press enter. So that's March 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20. We're still nowhere close to this $36,000. March 21st, 22nd, 23rd, 24th, 25th, 26th, 27th, 28th, holy cow, 29th, 30th, and March 31st. We see the amount of money that you would get on March 31st. That is a pretty nice amount. Very crazy how all of that multiplied to be such a big number. So with this option, 21,000 or sorry, $21,474,836.48. And remember, not only is that how much money you would have, you would be adding up all of the money from that you've gotten in the days before. So you would add this and this and this and this. So that is crazy how a penny doubling got to be a number that is this large. That is a huge number. Okay, let's think about an equation that we could have used as a shortcut instead of pressing enter so many times in the calculator. Let's think of an equation that we could have used as a shortcut that would have given us this $36,000. Okay, think about what is going on every time here. What are we doing every time here? We are adding 1,000 and adding 1,000. Okay, we're adding 1,000 every time. So we should be familiar with how to write an equation for this. Okay, we could start at $5,000 and we could add 1,000 for X number of days. We can check and see if that works for 31 days. If I start with $5,000, I could add $1,000 31 times, and that should give me that $36,000. That would have been a shortcut. Okay, you should be familiar with this notation, very familiar with this notation. We have a slope, a y-intercept, and a slope. We're adding 1,000 every time. Okay, let's come over here and let's see what is happening over here. I'm starting with 1 cent, and then what is happening every time? I am multiplying by 2. Multiplying by 2 every time. So instead of adding, over here we are multiplying. So we're not going to be adding, we're going to be multiplying. Now, when we were adding several times, the shortcut was to multiply by x. Okay? Over here, when we are multiplying several times, let's think about what shortcut we could use. What is the shortcut for multiplying by 2 several times? So, for example, instead of doing 0.01 times 2 once, times 2 again, times 2 again, times 2 again, what shortcut could I use instead of putting that times 2 in there 31 times? The shortcut for repeated multiplication would be to take the 1 cent and multiply it by 2 31 times to get this number. I would need to put the 31 in the exponent. The shortcut for multiplying over and over and over is the exponent. So I would start at 1 cent, I would multiply it by 2, and the number of days would be in the exponent. Okay? So just like you've been very familiar with writing linear equations like this, we've got a new type of equation now, and you're going to see this form for the equation. You're going to see this form for the equation. Okay, in our linear functions, we started with 5,000 and we're adding several times. This is a new type of function. The number outside of the parentheses is going to also be what we're starting with. And this 2 is like the slope, but it's not the slope because slope is what we add over and over. This 2 is going to be what we multiply over and over because it has the exponent. Okay, so let's look at this. So you'll notice these are called exponential functions. So this was linear. This is a situation that's exponential. And you should notice that linear functions go up at a constant rate. Exponential functions go up really fast because instead of adding, we are multiplying. And so exponential functions go up really fast. Okay, you should notice that the x was beside the slope for a linear function. Where is the x going to be for an exponential function? The x is going to be in the exponent for an exponential function. All right, so this is an example of an exponential function. How do I know it's an exponential function? The x is in the exponent. Okay, so what does that mean? That means this is a function where we're going to be multiplying by 2 over and over. What we want to do is we want to look at the shape that our exponential functions make. Our linear function makes a straight line, obviously. Exponential function, see if you can think about what shape this would make. Take a guess at what shape on the graph this would make. Take a guess at what shape this would make. Okay, let's see if your guess is correct. I need to plug all of these numbers in for x. So I'm going to do 2 to the negative 3 power, 2 to the negative 2. So go ahead and plug all of these in for x, because the x is in the exponent for exponential functions. Okay. I'm going to start with the ones that are easy to calculate. For example, 2 to the 0 power, we know what that is. We know that that is 1. I'm going to go ahead and put over 0 up 1 on my graph. 2 to the first power, we know that that is 2. 2 to the second power, we know is 4. And 2 times 2 times 2, we know is 8. Okay, so obviously this is not making a straight line. It is not possible to connect these points with a straight line. I can't connect any of them with a straight line. Okay, as I keep going, if I double again, I would get 16, 32. So on this side of the graph, it's going to keep going and going and going. So I'm just going to go ahead and connect these, and then it's going to get bigger and bigger and bigger, but this makes a curve. Okay. Now we're going to see what happens on the other side. 2 to the negative 1 power. We talked about how a negative exponent moves across the line and changes the sign. So this would be 2 to the first on the bottom. So this would be 1/2 or 0.5. Okay, so that's going to be about halfway between these two. 2 to the negative 2 power moves to the bottom to be 1/2 squared. So what is that? That is 1/4. Okay, that's going to be halfway between these 2 points. 2 to the negative 3rd power would be 1/2 to the positive 3rd, or 1/2 times 2 times 2, 1/8. That's going to be halfway between these 2 points. Now, it's very hard to, as they get smaller, it's hard to put the exact coordinates on here. But I want to think about what happens if I were to plug in -4, -5, -6, -7. What's going to happen as I plug in farther and farther away more negative numbers? If I plugged in -10, what if I plugged in -100? If I plug in these large negative numbers, what's going to happen? Does the output ever reach 0? Okay, so what's going to happen if I plug in -4? I'd get 1/16, and then 1/32, and 1/64. Okay, it's going to keep getting closer and closer and closer to this axis. Okay, but is it ever going to technically touch this axis? Am I ever going to get a 0 out? Well, let's think about if I had like 2 to the negative 500 power, or 1/2 to the 500 power. This is going to be a really large number. And 1 divided by, even if it's a really, really, really big number, 1 divided by 1,000,000 or 1 divided by 2,000,000. Is that ever going to be 0? No, it's going to get extremely small, but technically it is not ever 0. Okay, so when we keep this line going, to the untrained eye, it would look like this line is touching the axis. But we know that really it's just that the values are getting so incredibly small and close to 0, but not actually touching 0. And it's definitely not going to ever become negative or go below the axis. So does the output ever reach 0? Well, you're dividing 1 by bigger and bigger values, which makes the value get smaller and smaller, but no, it's never technically going to reach 0. Okay, it's going to be 1 over a million, and 1 over 3 million, and 1 over 5 million, and 1 over really, really big numbers, but technically it is not 0. So this is the shape that our graph will make for an exponential function. Okay, notice that this on this side, it's never going to come back up. It's never going to go below the axis. It's just going to keep getting smaller and smaller. Okay, you will see a lot of graphs like this in your upper level math classes, and you're going to see a lot of things where the graph keeps getting closer and closer and closer to something but never actually touches. A vocab word that you do not need to know for Math 1, but if you want to look smart in maybe Math 2 or Math 3, this is the vocab word for that. Okay, this is the vocab word for a line that the graph gets really close to but never touches. It's pronounced asymptote. It's a funny word, I know. So if you want to look smart in Math 2 or Math 3, you can say, oh, that's called an asymptote, which means that's the line that the graph gets really, really, really close to but never actually touches. You're going to see that in a lot of the graphs in your future math classes. In this particular example, and a lot of the graphs that we do, the asymptote is going to be y equals 0. That is, the x-axis is the line that it gets really close to but doesn't ever touch. But like I said, you don't have to worry about that until Math 2 or Math 3. So please grab the toolkit, toolkit 26, or whichever one says linear versus exponential functions. And what we're going to do is we're going to compare linear and exponential. So in this top corner, I'd like for you to put linear. Okay. And for this one, put exponential. And we're going to compare what we've learned so far about the two. What does the equation of a line look like? Equation of a line, you should know this very well. Looks like y equals mx plus b. Okay, we know that the m is the slope and the b is the y-intercept. And there are no exponents in our linear equations. Linear equations do not have exponents. The x is beside the slope. Okay, so the m is the slope. The m is the slope, what is being added every time, and the b is the y-intercept. Okay, we saw one equation of an exponential function. Well, we've seen two. Back on the discovery, this is the basic form of an exponential function. We have a number inside or outside the parentheses, and what did this 0.01 represent? It represented the y-intercept. Okay, the y-intercept was outside the parentheses, and then we had a number inside the parentheses. That was under the exponent. Okay, so the equation, how we're going to write that is y equals a parentheses b to the x power. A parentheses b to the x power. This is the form that you're going to be seeing now instead of this one. Well, you'll still see this sum, but this is a new form you need to be as familiar with as you are with this one. Okay, we said that the a is going to be the y-intercept. Now, exponential functions do not have a slope because slope is what is being added every time. Okay, so this b is not going to be the slope. It's similar to the slope, but it is not going to be the slope. What it's going to be called is the growth factor. Factor has to do with multiplication. And since we're multiplying over, this is called the factor. Okay, so what we add every time is called the slope. What we multiply every time is called the factor. And there's no exponent for a linear function. Exponential functions do have an x in the exponent, or an n, or a variable. Whatever the variable is in the exponent. Okay, so you need to be very familiar with writing an exponential equation like this. Okay, if we look at a table for a linear function, the y values in the table like this, what happens every time they are adding, versus in an exponential function, they are multiplying. So the y values in the table for a linear function are adding or subtracting. They are constant. They're adding or subtracting the same thing every time. Now, the y values in the table for an exponential function, if it's growing, it's going to go up or down by multiplying. Now notice, I do not say multiplying or dividing. I'm going to talk about why that is. Okay, we're not going to really use dividing too much in this unit. We're just going to use multiplying. And you'll see why in just a minute. Okay, we looked at recursive rules back in Unit 2. You should know that a recursive rule looks like a sub n, make sure that n is a subscript, equals a sub n minus 1, and we either add or subtract to get from one term to the next. So what's going to happen with our recursive rule for exponential? Well, instead of adding or subtracting, we're obviously going to be multiplying. So instead of putting a sub n equals a sub n minus 1 times something, we're actually going to put the number in the front of the previous term. So what does this mean? Any term is something times the previous term. Okay? Any term is something times the previous term. We're going to have some more practice with this type of recursive rule in a couple of days. And the shape of a graph. If we have a linear function, obviously it makes a straight line, either in a positive or negative direction. But we looked at exponential functions and we saw that the shape it makes is a curve. Okay, and this is what the curve looks like. It does not come back around here. It keeps getting bigger and bigger on the right side. On the left side, it does not curve back up. It keeps getting closer and closer and closer to a number that it makes. Okay, so this is a line. I actually call something that makes this shape, it's just called an exponential growth curve. It doesn't have a fancy name. So I actually call it banana shaped because it looks sort of banana shaped to me. That's not, of course, the fancy term for it, but I call a graph shaped like this banana shaped. So I call exponential functions banana shaped. Okay, so that's some of the basic differences between a linear and an exponential function. Okay, let's head back to the discovery and look at 6. Whenever Patricia gets angry, she takes a piece of paper and tears it in half, and she throws the other piece away. So after she gets angry one time, she has half of the paper. After 2 times, she's left with half of that, which would be a fourth, and then half of that again. So we tear it in half, and in half, and in half, and in half again. So we said when she gets angry one time, she is left with half the paper. When she gets angry 2 times, she's left with half of that, which is a fourth. When she gets angry 3 times, she's left with half of that, which should be 1/8. So let's think about what the rule would be for this function. Okay, we said the format would be a times b to the x. A is the y-intercept. Well, so when it's 0, how much paper does she start with? She starts with a whole. So this is going to be 1, and what am I multiplying by every time? Times 1/2 to the x power. Okay, 1 times 1/2 to the x power. If I'm multiplying by 1, does it really matter? No, so the 1 does not have to be there. It can be there, it doesn't have to. So this is 1/2 to the 0 power. This is 1/2 to the first power. This is 1/2 to the second power. And this is 1/2 to the third power, or 1/2 times 1/2 times 1/2. Now, technically, you can't get angry negative amount of times, but what we're going to do is we're going to pretend like you could, just so we can figure out what shape this graph would make. Okay, so if I had 1/2 to the -1 power, that means I need to give the 1 the -1 exponent, and I need to give the 2 the -1 exponent. Okay, what does that mean? That means the 2 flips across the line and change the sign. The 1 flips across the line and change the sign. This just gives me 2. Okay, 1/2 to the -2 power. This would be 1 to the -2 power and 2 to the -2 power. You distribute the exponent to everything inside. This moves to the bottom to become 1 to the positive 1, or sorry, 1 to the positive 2, 2 to the positive 2. That gives me 4/1. And 1/2 to the -3 power. I could distribute the exponent, 1 to the -3, 2 to the -3. This moves to the bottom to become 1 to the positive 3. This moves to the top to become 2 to the positive 3. So 2 times 2 times 2 gives me 8. Okay, I'm going to graph these points. -3 up 8. -2 up 4. -1 up 2. 0 up 1. Okay, so I have 1/2, 1/4, 1/8. And let's think about if she gets mad 4 times and 5 times and 6 times. So that's going to be 1/16 and 1/32. Technically, would there ever be no paper left? Would there technically ever be no paper left? No, we have the same thing over here. It's going to get closer and closer and closer and closer to 0. But technically, no, there's never going to be no paper left. Okay, no, because you can't multiply something by 1/2 and ever get 0. The output is never 0. Okay, because 1/2 times 1/2 times 1/2 times 1/2, even if you do that a million times, yes, it's going to be extremely small, but technically there's never no paper left. Okay, and then as I keep plugging in -4, -5, and -6, we're going to keep getting larger and larger values out. This is going to keep getting bigger forever. So let's talk about what we notice about this graph in this example versus the one at the top. What do you notice? You should notice that this one is getting bigger over time, and this one is getting smaller over time. You should notice that these are opposites of each other. So take a look at this. 8, 4, 2, 1, this is opposite. We got the same thing, but backwards. And let's look at what our equations were. Our equations were 2 to the x power and 1/2 to the x power. Those are opposites of each other. Okay, so we need to decide what is it that's going to make a graph increase, an exponential graph increase, and what is it that's going to make an exponential graph decrease. So take a look. If we have 2 to the x and 1/2 to the x, so you would probably guess, so we know that 2 to the x would increase and 1/2 to the x power would decrease. Okay, so what do you think that 3 to the x power would do? It would increase, okay, and 1/3 to the x power would decrease. So what do you think the rule is that's going to make it increase or decrease? You're probably thinking if it is a whole number, it's going to increase, and if it is a fraction, it is going to decrease. Okay, that is a good guess, but unfortunately, that's not always the case. Okay, I want you to think about, what if I had 1.5 to the x power? This is a graph that would increase. If the factor is 1.5, it would increase, because if I multiply 1.5 to the first power and then 1.5 to the second power and 1.5 to the third power, what's happening every time? It is getting bigger. Okay, so if it is a decimal or a fraction, that does not necessarily mean it gets smaller. We need to think about what the cutoff is for multiplying to make something get bigger or smaller. And to do that, let's think about, what could I multiply by to make something stay the same? What could I multiply by to make something stay the same? If I multiply by 1, something would stay the same. If I multiply by something bigger than 1, it will get bigger. If my factor is bigger than 1, then what I'm multiplying by will get bigger. If it is smaller than 1, it would get smaller. Okay, so the cutoff is 1. The cutoff is 1. So the number below the x is a 2. That's bigger than 1, so we have a situation that's getting bigger. If we're multiplying by something smaller than 1, it's going to get smaller. So that's why it's not just a fraction or a decimal. That is the rule. All right, so back on this toolkit. The function where it gets bigger is going to be exponential growth. And if it gets smaller, it's going to be an exponential decay situation. So instead of saying that we are multiplying or dividing, instead we're going to talk about what we could multiply by to get bigger and what we could multiply by to get smaller. Okay, so the equation, we're going to have a times b to the x, but a is still going to be the y-intercept, but this time b is going to be called the decay factor. So I'm still multiplying. So how can we tell if something is a growth factor or a decay factor? A growth factor is going to be bigger than 1. A decay factor is going to be smaller than 1. Okay, and still we have x in the exponent for exponential decay. So linear, we had positive or negative to tell whether we were going up or down, because we were adding, and adding 0 is the cutoff point. But since exponentials have to do with multiplying, 1 is going to be our cutoff point. We're going to be multiplying by a number bigger than 1 or smaller than 1. So the y values in the table are going to go down by multiplying a number smaller than 1. And exponential growth is a number larger than 1. Again, if you multiply by 1, something stays the same. Okay, the recursive equation is going to look like this, but let's talk about the difference in what number is going to be in front of the previous term. If it's an exponential growth situation, then we're going to have a number bigger than 1. If it's an exponential decay situation, we're going to be multiplying by a number smaller than 1 in between the terms. And we saw that the banana-shaped graph is starting out big and then, that's not good, starting out big and then getting smaller. Okay, this is not going to come back around. It's going to keep getting larger and larger. On this side, it's going to keep getting closer and closer and closer to whatever number it is approaching. Okay, so these are the differences that you need to know between linear and exponential. One important thing I want to point out, since we're not thinking of dividing, we're only doing multiplying, is that if there is a situation where something is dividing by 3, okay, and we want to make dividing by 3 in terms of multiplying, I hope that you know that dividing by 3 is the same as, what could I multiply by instead of dividing by 3? So for example, if I had 30 in the calculator, instead of dividing by 3, what could I multiply by? Hopefully you know that dividing by 3 is the same as multiplying by 1 over 3. Or dividing by 4 is the same as multiplying by what? 1 over 4. So if there is a situation that you see that is dividing by 10 every time, obviously that's going to be exponential decay. What could I multiply by instead of dividing by 10? I can multiply by 1 over 10. Okay, so this is something very important for you to know, that multiplying by 1/3 is the same as dividing by 3. Think about if you divide something into 2, that's the same as multiplying by half. You have half of it. Okay, so that's very important for you to know. All right, back on the discovery, I'd like for you to try number 8. So pause the video for a minute, and you can write which ones are linear, exponential growth, or exponential decay. You can abbreviate exponential as EXP. So see if you could tell which one of these, some of them are recursive, some of them are functions, some of them are situations. See if you could tell what is linear, exponential growth, and exponential decay. Okay, so pause the video and see if you can figure out which is which. Okay, hopefully you paused the video and went ahead and tried to figure out which of these are linear, exponential growth, and exponential decay. Let's take a look at letter A, y equals 9x. This has a y and an x, and the x is not in the exponent. So hopefully you know that this is a linear. This one is linear. Okay, letter B. This has a sub n, so this is obviously a recursive rule. For the recursive rule, we want to look and see if we're adding or subtracting to the previous term or if we are multiplying. And right here I see that if this is the previous term, I am multiplying the previous term by 5.8. Multiplying makes it exponential. Then we need to decide if it's exponential growth or decay. Well, how can we tell? We figure out if we're multiplying by a number bigger or smaller than 1. Since this number is bigger than 1, it is exponential growth. Letter C, this is a function, an explicit function, and I see that the x is in the exponent. Since the x is in the exponent, it is exponential. And the base, the number that is being multiplied over and over, is bigger than 1, so this is also growth. Okay, again, x is in the exponent. This is an explicit function. If x is in the exponent, it is exponential. And since I'm multiplying by a number smaller than 1, it is exponential decay. Okay, letter E, this by the shape of this graph, it's a curve, so it's obviously not linear. It's exponential and it's getting smaller, so it's exponential decay. Okay, looking at this, let's see what's happening. You have to look at the y values. When the x goes up by 1, what's happening to the y's? It adds 15. Does it keep adding 15? It does. So since it is adding, it is linear. If it's adding in between terms, the same number, it is linear. This one subtracts 16. Does it keep subtracting 16? No, it does not. So it must be multiplying by something. I could see here that it is dividing by 2. What is that the same as? That's the same as multiplying by 1/2. So this is exponential because it's multiplying. Since it's a number smaller than 1, it is decay. Letter H, I have a recursive rule. And I see that it is subtracting to the previous term. So since it is subtracting the previous term, it's linear. That's a little tricky because a lot of people, when you see a decimal, you think it's exponential, but not always. This one is subtracting 0.7, so it's a linear function. Okay, Charles's allowance increases by 25. Does that mean it adds, subtract, multiply, or divide? Increases means it's adding 25. So since it is adding, that is linear. And then Dana's allowance, if it doubles, that's multiplying by 2. If it's multiplying, it's exponential. And since it's a number bigger than 1, it's going to get bigger, so it is exponential growth. Okay, number 9. Aaliyah has a secret, and she texts it to 3 of her friends, but she tells them not to tell anybody. So her 3 friends know that they can share the secret as long as they say don't tell anyone. Let this be a life lesson that just because you tell somebody not to tell somebody, chances are they're going to tell somebody. So Aaliyah's 3 friends text 3 of their friends a minute later, and the pattern continues. Make a table and equation representing the situation. Then find out how many texts will be sent 10 minutes later. So before we do this, I want you to think about what your guess would be. How many texts would you guess would be sent 10 minutes later? So just come up with a random guess of how many texts you think would be sent. Okay, so what we're going to do is, so we have the number of minutes. One column is going to be the number of minutes, and one column is going to be the number of texts sent. Okay, technically, at the beginning, technically there'd be one person who found out that this is Aaliyah. Okay, after 1 minute, Aaliyah texts 3 of her friends. After 2 minutes, these 3 friends are each going to tell 3 of their friends. So how many total texts would be sent the second minute if 3 people each tell 3 people? If 3 people each tell 3 people, that would be 9 texts sent. Okay, and then we keep multiplying that, and that would be 27. So, by the way, this says, remember that this is not how many texts, this is just how many texts were sent, not how many total people know. If we wanted to know how many total people knew, we would have to add this 1 plus 3, plus this 9 plus this 27. All right, so let's see if we can figure out a function instead of keeping the table going. Let's see if we can find a function rule. Okay, obviously this is exponential. Why? Because it is doing what each time? It is multiplying by 3. Okay, so my y-intercept is 1. A lot of times in this unit, the y-intercept is going to be 1. This 3 is what we are multiplying by. Do you remember what this number inside the parentheses below the exponent is called? It's not the slope. It's similar to the slope. It is the factor. Okay, so 3 to the 0 power would be 1. 3 to the first power is 3. 3 squared is 9. 3 to the third power is 27. So to figure out 10 minutes later, I would need to plug in a 10 in the exponent. So 3, and you could do 1 times 3, but that isn't that important. All right, let's figure out, and remember, this is not how many total people know, this is just how many texts would be sent at that minute. So 3 to the 10th power would be, wow, that's a really big number. Was your number that you guessed close to that? 59,049. Again, that is just how many texts were sent, not how many total people know. And I think a lot of you know you could probably send a text to 3 people in faster than 1 minute. And you could probably send a text to more than 3 people. This is just telling 3 people. Some of you have a lot more people you could tell. So keep in mind how fastly things can spread and to how many people it can spread to. That's the power of exponential growth. Number 10, you take 600 milligrams of ibuprofen. It has a half-life of 2 hours. What does half-life mean? That means every 2 hours, half of it remains. Okay, so if we start out at 0, for 0 hours, that's starting out at 600, and then half of it would be 300, and then another 2 hours, half of it would be 150. Then half of that is 75. Half of that is 37.5. Would there technically ever be none of the ibuprofen left in the bloodstream? There wouldn't. And that's what happens when you take medicines and drugs. They stay in your bloodstream. They have what's called a half-life. So they decay, but they never technically get to 0. Now, of course, it is going to get to a point where it's too small to be picked up on any sort of test, and there might be 0.000000 something left, but it's never technically going to be 0. All right, number 11, the population of rabbits is tripling. What does tripling mean? It means multiplying by 3 every year. It says there's 40 rabbits to begin with. Write an equation to model the number of rabbits after X years. Y is the number of rabbits. Okay, so what's happening? We're starting with 40 rabbits. What's happening every time? We're going to multiply it by 3 the first year, multiply it by 3 again for the second year, multiply it by 3 again, and again every year. So the shortcut for the number of years, the shortcut for multiplying by 3 several times would be what? It would be to put the x in the exponent. Okay, so after 11 years, I would need to plug in 11 for x. So that would be 40 times 3. It's going to multiply by 3 11 times. So I could do 40 times 3 times 3 times 3. I could do this 11 times. But instead of doing that, what could my shortcut be? It could be to raise it to the 11th power. Hopefully you know that putting an exponent in, you need to use this right here. And we can see, would you expect that 40 rabbits tripling would get to be a number this large? Okay, that is over 7 million rabbits. This is the power of exponential growth. Sometimes things people talk about you want your money to grow exponentially, or you want your church attendance to grow exponentially, and you can see that exponential growth is a lot faster. In 2004, there were 400 fish. Every year, 3/4 remained. How many fish remain this year? Okay. Let's cross out that sentence. Okay, write an equation. So y equals, what's the starting amount? 400. And what am I going to do every year? Since it says 3/4 of, and of means multiply, I'm going to multiply it by 3/4. If I multiply it by 3/4, is this going to get bigger or smaller? If you multiply by 3/4, it's smaller than 1, so it's going to get smaller. So every year I'm multiplying it by 3/4. The shortcut for doing that over and over and over would be to put the x in the exponent. Okay, so let's figure out how many would be left in 2020. I would multiply it by 3/4, and x is the number of years after 2004. So how many years after 2004 is the year 2020? That would be 16 years later, I believe. So we would start with 400 and we'd multiply it by 3/4 and 3/4 and 3/4 every year. The shortcut for doing that over and over and over would be to raise it to the 16th power. And we could see that there it says round to the nearest whole fish. There would be 4 fish left. So you can see just as exponential growth gets really big, really fast, exponential decay is going to start off going down a lot, but then it's going to not be so fast after a while. Okay. Leslie weighs 354 pounds. Each month she loses 4 pounds. So if we're losing 4 pounds, what are we multiplying by here? Or are we multiplying? Actually, this is subtracting 4 pounds. So is this going to be a linear or exponential? This one is going to be a linear situation. So her weight, y, after x months, we would start at the y-intercept would be 354. What's going to happen every month? We're going to subtract 4, subtract 4, subtract 4, subtract 4. The shortcut for subtracting over and over and over, it would be to multiply. So the x is going to be at the regular level. We'd subtract 4 and put the x at the regular level, not in the exponent. So after 2 years, I would start at 354 and I would subtract 4. How many times would I subtract 4? 24 times. So if it's subtracting, this is a linear situation, not exponential. Adding and subtracting is going to be linear. Okay, and that would be 258. So hopefully you see the difference between our linear situation and our exponential situations where it's multiplying over and over. Lastly, let's take a look at how to graph these. Okay, these are all exponential. These have x in the exponent. So the first thing I'm going to do is I'm going to look at the y-intercept. What is the y-intercept of this function? The y-intercept is 2. So where can I put this in this table? Well, the y-intercept is where x equals 0. So I'm going to put a 2 there. Okay, it starts at 2. Okay, what does the 1/4 tell me? What is that 1/4 called in the parentheses? That is called the decay factor, and that tells me what is being multiplied each time. Sort of like slope, what was being added every time. The decay factor is what is multiplying every time. So I'm going to take that 2 and I'm going to multiply it by 1/4. Okay, if you have $2 that you split between 4 people, you'd each get 50 cents. So I could do 2 times 1/4, and then I can multiply that by 1/4 again. And I don't care if you put these in as a decimal or fraction. And I can multiply that by 1/4 again. And that is 0.03125. Okay, so I start at the y-intercept and I say what it is multiplying by every time. But going backwards, if I need to go backwards, what would the opposite of multiplying by 1/4 be? I hope you know that multiplying by 1/4 is the same as dividing by 4. So if we're going backwards, we would need to multiply by 4 each time. Okay, going backwards, we would multiply by 4. So 2 times 4 would be 8. 8 times 4 would be 32. Okay, so I could see it's dividing by 4 all the way down with the y-intercept being 2. You could have just plugged in -2, plug in -1 for x, plug in 0 for x, plug in 1 for x. You could do that each time. Or I think it's easier to start at the y-intercept and then multiply all the way down. Okay, so -2, 32 is going to be way off the graph. It says don't worry about the points that aren't on the graph. -1 up 8, 0 up 2, 1 up 0.5, 2 up 0.125, and so we know these are going to get closer and closer to the axis. So we said 32 is going to be way up here, and I'm going to connect these points. And I know if I'm graphing and there's an x in the exponent, it is not going to make a straight line. It would be banana shaped. This is going to keep getting bigger and bigger and bigger. This is going to keep getting smaller and smaller and smaller, but never 0. Okay, 3 to the x power. Let's think about, over here I started with the y-intercept of 2. There is no y-intercept written here. So we need to figure out if this is a times b to the x. We need to figure out what number would be here. Okay, so who knows what number would be here? Would it be a 0? 0 times 3 to the x power? 0 times 3 to the 1 power, 0 times 3 to the 3rd power. Will that work? No. What number does not change for multiplication is 1. Okay? So that's a little bit different because in our linear functions, y equals mx plus b, if the plus b was not written, what was our y-intercept? It was 0. But our exponential functions, if the y-intercept is not written, are going to be 1. Okay, and another way you could figure that out is we could look at what is 3 to the 0 power. Anything to the 0 power is 1. 3 to the 1st power. Okay, so what's going on every time? It is multiplying by 3. It's going to multiply by 3 all the way down. Times 3 times 3. And what would happen going backwards? I would multiply by 1/3 or divide by 3. It's the same thing. Okay, so going backwards, this would be 1 over 3. 1/3 times 1/3 or divided by 3 would be 1 over 9. And then 1 over 27. So I've got -2 up a 9th. -1 up a 3rd, over 0 up 1, over 1 up 3, over 2 up 9, up to 27. It's going to be way up here. Okay, so make sure that your graph, I could tell by looking at this equation, since the base was bigger than 1, that it was going to be growth. I could tell that since the base was smaller than 1 here, it was going to be decay. And they're all, if they have an x in the exponent, are going to make this banana shape. Okay, letter C, I'm going to start with the y-intercept. The y-intercept is 8, so I'm going to put that at the 0. The y-intercept is 0. And this tells me what's happening every time is that it is multiplying by 1/2. Multiplying by 1/2. Okay, so we have 8 times 1/2, 4 times 1/2, 2 times 1/2. And if we're going backwards, what's going to happen? It would be the opposite of multiplying by 1/2 would be dividing by 1/2, which we know is the same as multiplying by 2. So that would be 16 and 32. So it's multiplying by 1/2 or dividing by 2 all the way down. -2, 32 is going to be way off the graph. -1, 16 is going to be off the graph. Over 0 up 8. Over 1 up 4. Over 2 up 2. Up 1. 3 up 1. What would come next if I multiplied it by 1/2 would be 1/2 and then 1/4. Okay, so that gives me a picture. Make sure, remember, it's not going to make a straight line. It's going to make a curve. It's always going to make a curve if it has an x in the exponent. Okay, lastly, this is a recursive rule. This is a recursive rule. So what's happening in between the terms? Each term is 3 times the previous term. This tells me that the first term is 9. Take a look at this. Where should I put the first term in my table? Is that the y-intercept? No, that is going to go for the first term is 9. If I give you a recursive rule, the first term would go where x is 1. Okay, and then what's happening every time? It is multiplying by 3. So multiplying by 3 would be 27, and then 81. Okay, what would I need to do going backwards? I would need to divide by 3 or multiply by 1/3. Okay, divide by 3, 3 divided by 3, 1 divided by 3. Okay, so each term is 3 times the previous term. The first term is 9. So let's graph that. I've got -2 up 1/3, -1 up 1, 0 up 3, 1 up 9, then we go up to 27 and 81. It's going to shoot up really quickly. Okay, it's hard for me to draw graphs on this, but that is what it would look like.